Good afternoon, fancy meat computers. I hope everybody's doing well. Five people currently viewing. Crunchy breaths, yes. Oof. So I'm feeling mostly better, but, the cold still, it takes a while to sort of clean yourself out after a cold, especially if, you've had to basically work the whole way through it anyway, because, deadlines be deadlines, am I right? Yeah, so, how are we doing today? How's everybody doing today? I hope that everybody is, have things let up at all with you guys? Is this a better week than last week? Happy Tuesday. Happy Boxing Day for All Saints Day. No, it isn't a better week? Well, this week is hell, but you're surviving. That's the spirit! Assignments never stop. I mean, yeah, this is true. And, they will stop. Assignments will stop when you're dead. Just like the beatings will improve until... no! The beatings will continue until morale improves. Let's see. 3 SD3A2 on Monday. My assignment Sunday. 3DB Sunday. 3 GC Wednesday. 2 MC... No clue. 3 IO3 presentation tomorrow morning. Oh, and don't forget Project 2 is due today as well. The 3DB3 assignment for this week took 12 hours. Yikes. I'd rather graduate before I die, thank you very much. Well, that's the hope. If you've been doing a PhD as long as I have, that hope starts to wane somewhat. But, real tears. Yeah. Well, at least we didn't have that midterm I was promising this last weekend. Because I had originally, I think, scheduled the midterm that I was going to have for this class this last weekend. So that would have just been, I think people probably would have just died. It's just like, oh, that's it. Just like that. Too much work. Gotta go. See you in the afterlife. Just like that. Anyway. So, we should get on with it. I shouldn't have too many expectations for the number of people who are going to come to class then, eh? That's okay. As long as we have the few, the proud, the 10, then I think we'll be okay. But, so we were talking last time about preservation, the preservation of the preservation property over substitution. And it's a little bit tricky. So just to remind ourselves, the preservation property is that if we have some term which is typed T, the type T, and we have some term S which is typed S, then we can say that upon substitution of X for S, T retains its type. So the idea is that the typing of the term T is preserved by substitution. Now this is in contrast to the like the previous in the previous semantics, we did preservation of preservation of typing under conditions of evaluation, right? So the evaluation semantics are one thing. The substitution semantics are an entirely different thing, right? As I'm sure all of you are finding out with Project 2. So it is insufficient in the present time to demonstrate preservation for just the specified semantic rules that we have established for our typed lambda expressions. Pardon me. We also need to prove that that well typing and well typedness is preserved by substitution as well, right? Because we use substitution. Substitution is part of our semantics, so we need to demonstrate preservation over it in order to have some assurance that preservation holds for simply typed lambda calculus. In order for it to be type safe, we need to prove it for substitution as well. So we had been proceeding by case analysis over our typing rules. We'd done t-true and t-false, because remember, the subset of, this is not just the pure lambda calculus. We are also working in the Boolean component of UAE so that we have some base type, and so our language isn't degenerate and has no valid types in it because there's no base type. So, we talked about t-true and false. We had talked about t-if. But perhaps we should reconclude our previous conclusion. So, it turns out to be helpful to just focus on evaluation rules and forget the difference between call by value and call by and normal order when doing P2. Yes! Actually, that's a really, really good piece of advice there. You don't have to have the difference between normal order and call by value memorized because it's encoded directly in the semantic. If you just follow the semantic rules as given, you don't actually have to worry about the difference between normal order and call by value because it's automatically the thing we expect it to be. Very good comment. Thank you. So, let's consider t-if. If we have just used the typing rule t-if, then we know that t must have the form if t1 then t2 else t3. We further have the three antecedents. Am I muted? Can I be heard? Hello? Oh, it's coming fine through. It's coming through fine for me. Maybe check your volume. Okay. So, in addition to knowing the form of the term, we're also given the information encoded in the antecedents. So we know that given gamma and s, or x typed s, t1 evaluates to bool. Given the same context, t2 evaluates to t, and so does t3. Using the induction hypothesis, we also know that under substitution, t1 will retain the type bool, t2 will retain the type t, and t3 will retain the type t. So, from here, it's really quite easy. I don't think we actually did substitution rules expressly. I don't know if we ever formalized them specifically for if statements, but it's about what you would imagine. You just, similarly to application, you take the substitution and you pass it to each of the three arguments. So, given that the substitution passes down, given that the typing of the antecedents is preserved over the substitution because of the induction hypothesis, we can conclude that you can just reapply the typing rule t-if to re-derive the fact that t must have type t after substitution. Which is, you know, that's probably one of the easiest ones we're going to do. The tab was muted for some sudden reason. Yeah, I'm not sure if I'm a huge fan of tab muting. You know? I prefer that websites just don't play music at me or ads, you know? Anyway. So that's t-if taken out of the picture. Let's talk about t-var. So, if t-var is our typing rule, then we can immediately state that t must be some variable z. We're calling it z because we're trying to pick a variable name that's not currently in use by the preservation theorem, because, you know, it can be any variable, right? We also know that z typed t is an element of gamma, comma, x typed as s. So it's an element of the typing context, right? Because that's an antecedent. That is to say, we know t to be some variable. We've picked the name z for no particular reason. We know that z has type t via the antecedent of the typing relation. If we refer back to our substitution semantics, the only factor affecting the substitution of the variable for a term is whether that term is, in fact, the variable itself. Remember, back in our substitution semantics, that the only difference when you're talking with just a straight variable is whether or not x and y are the same thing, right? You substitute if x is the thing that's being substituted, and or you substitute if the variable is the same thing as the variable being subbed out, and you leave it alone if it's not. So we can case analyze those two cases. Consider first the case where x is equal to z. If we substitute x for s in z, that would then evaluate to s. And since we know that x is equal to z and z is equal to t, we also know that x is equal to t. So, via the uniqueness of types, x being typed s and t being typed t means that x is equal to t. So that's kind of like, I've had to pull in some, we've had to pull in more like secondary facts for this one than normally we have to. But it makes sense, right? So we know that, we know from this case that z and x are the same thing. We know from this that z and t are the same thing. We can therefore conclude that the thing we're subbing, like, we can conclude that x is equal to t. It says equation 17, but isn't it supposed to be 20? What is equation 17? That's a good question. Boy, I have to go a long way back. Yep, that means that's supposed to be 20. Whoops. Must have added some formulas. I should really do, like, refs instead of hard-coding my reference labels. Anyway. So we know that s is equal to t, and we know that x is equal to t, and we know that z is equal to t. So if we perform all of these substitutions in our original preservation theorem, right, what we end up with is gamma, comma, s typed x typed s demonstrates x has type s. That's, like, trivially true. And gamma demonstrates that s has type s. Right? So, can we conclude from that gamma proves that s has type s? Why, yes, we can, because it's one of the antecedents to this implication. Right? It's like, does x and y imply x? Yes! That's how logic works. So our conclusion here is explicitly one of our premises. So it works. Wonderful. Now, consider the case where x does not equal z. In that case, if you try to substitute x for s, z would evaluate to z, and from there to t. So, in this case, basically we've left the thing alone. And because we've left the thing alone, we know that it'll still have its type, right? Basically, if we sub that in, starting with a context, so we have it as a premise, gamma and x typed s gives us t typed t, and it's true that gamma gives us s typed s, although that's not relevant because we're not even using s. Can we show from this that gamma yields t colon t? By applying the weakening lemma to our conclusion has the first form of as the first premise. So that is to say, we can add stuff using the weakening lemma, right? So we can transform this to have the same form as this guy, and therefore we're in the same position. Any questions about that? We cool? Hopefully this is cool. I promise the next topic is going to be more interesting than this. So, we have to get there, though. So, now let's consider probably what's going to be the most complicated of these, which is T-abs. So, this is not the sort of derivation that I would expect you to derive on something like an assignment. The abstract syntax is the worst part of this. Logically, it makes sense. Yeah, it's just like things get real complicated when you're throwing gammas in all over the place, right? But, you know, it's a necessary evil, you know? Yeah, so... Oof. My ratio just died. I need more than 8 votes. It's like, you need more than 8 viewers! So let's consider the typing of the abstraction operator, right? So if we're analyzing T-abs, we immediately have that T is some lambda y having type T2 over some term T1. We know that the type is going to be T2 yields T1. And we know that gamma added with, if we take gamma and we add x having type S and y having type T2, that will yield T1 having type T1. The term T1 having the type T1. By our meta rules of substitutions in lambda expressions, we derive the following. X does not equal y, and y is not an element of the free variables of S. And this becomes important. Again, if you're having difficulty with the material, I require a question to answer, because I don't know what difficulty you're having unless I get some words on paper. Yeah. So, full screen. Yes, sorry. There we go. So, using the permutation lemma on the rightmost equation, we can rearrange this slightly. So this is where we're going to use the permutation lemma. We can say, so we basically just swap the positions of these two guys, right? So, fine. We can then use the weakening lemma on gamma proves S has type S to get gamma and y having type 2 yields S yields type S. Or S has type S. then by the induction hypothesis, we can say that gamma plus y as type 2 gives us that T1 having type 1 if we substitute x for s over it. Like, yeah. So recall our typing rule for abstractions, right? This is basically our typing rule for abstractions, the antecedent, but with a substitution being preserved over it. So, applying this to equate... Oh, did I get the references messed up again? Yeah, I think I did. So, anyway, if we apply this equation... So we have this as an antecedent, which means that we can derive the following as a consequent from the typing rule by application of T-abs, right? So we know that gamma demonstrates that if we have lambda y as type 2, and we have the substitution now over T1, that will have type T2 yielding T1. The definition of substitution is that when we perform a substitution and x is not equal to y, that substitution gets passed down to T1. So essentially, you can see that we have derived the inner term here. So what's strange and interesting about this particular derivation is that we're not using the evaluation rule for abstractions in order to sort of say, and then it must evaluate this way. We're actually like applying typing rules, and then, oh look, if we apply the substitution semantic and we apply the typing rules, we end up with the substitution occurring in the same way as the evaluation rule, right? So, blop. So the left-hand side of the left-hand side is of type T2 yields T1 from our original case analysis. The right-hand side has the same type via equations. Via equations, the last four of them. Therefore, well-typedness is preserved by substitution in this case. Are you all satisfied that this has demonstrated substitution, that typing is preserved under substitution for lambda abstractions? Have you been satisfied by the proof? Hopefully. We have just one more to go, and then we're on to our next great adventure. So, finally, let's consider T-app. Are you not entertained? You should be. I'm a very entertaining person. I'm wearing the bow tie and everything. So, T-app is actually going to be pretty easy in general. Hopefully. It's easier than the last one anyway. So, for T-app, we immediately have the following. We know that T is T1 applied, T1 with T2 applied. We know that the type of T1 is T2 yields T1, and we know that the type of T2 is T2. We also know that the type of this thing in total has got to be T1, right? It's like, you got to have a function from T1 to T2, you got to apply T2 to it, and then you get T1 as a result. That's application. Via the induction hypothesis, we also have that when we perform substitution over T1, we still have the type T2 yields T1, and when we perform substitution over T2, we still get T2 as the type. So, recall that the typing rule for application, with some slight renaming, you know, removing the T11s and that type of thing. So, T1 having type T2 yields T, and T2 having type T means that T1, T2 has type T. And recall our substitution rule for applications. When we substitute over an application, we just apply the substitution to both of the subterms. By applying T-app to our induction hypothesis, we determine that the type of X, the type of T, the type of the whole term with the two substitutions applied must still be T. Therefore, the typing is preserved under substitution in the case of function application, quod erat demonstrandum. We have covered all of our cases. We have demonstrated that typing is well typed. If something is well typed, then that is preserved under substitution. Bam! Any questions? Questions, questions, questions. If you don't answer a question, I can't answer your questions. If you don't ask a question, I can't answer your questions. Blammo. Running test cases on your Project 2 code. Yeah, that's not anything to do with the lecture. Okay. So, moving swiftly on, we move to topic 9, external versus internal languages. This is going to be a fun one. We're going to start talking about real stuff now. So, we're going to talk about the Curry-Howard correspondence, erasure and typability, church style versus Curry style, atomic types, formalizing sequencing, ascription. I keep wanting to pronounce it ascription, but it's ascription, because if you pronounce it ascription, that means without scription, whereas the root of this is to ascribe, so it's ascription, not ascription. And then we're going to talk about let bindings. So, the Curry-Howard correspondence. Laugh at my joke, peasants. Is that referring to the famed Haskell B. Curry? That is referring to the famed Haskell B. Curry. I don't know what Howard's first name was. Like the Howard of the Curry-Howard correspondence. Thank you. Thank you for laughing at my funny joke. So, reasoning with typing relations. Todd Howard. Thank you. So we're gonna take this lecture is gonna, this week we're gonna be like kinda skirting, like we're not gonna be doing as much heavy math. Todd Howard, creator of Skyrim. Damn it! Not that Howard! Ugh. Oh my goodness. Now I have been thoroughly trolled by the chat. Thank you. So, oh my god. Now I have to look it up. William Alvin Howard. That's a great name. William Alvin Howard is a proof theorist best known for his work demonstrating formal similarity between intuitionistic logic and the simply typed lambda calculus that has come to be known as the Curry-Howard correspondence. Yes, that's the Wikipedia description. So we're going to talk, like, in more loose terms today, this week. This week is going to be a little less heavy on the math and a little more, like, heavy on the concept, which I think everybody will appreciate the break, including myself. So, someone clip that, yeah. So, let's talk about the typing relation, right? You may have noticed that with the type constructor, our arrow, we have a mechanism for introducing it, which is t-abs, and then we have also a mechanism for eliminating it, right? If you go on to study advanced topics in type theory, the stuff that's well beyond the scope of this course, you will find that many type constructors use introduction and elimination rules. This is actually how we often talk about them. But what else do we have rules for introducing and eliminating? Big think! That's right, folks. It's our old friend implication from propositional logic. So, when we're doing natural deduction, which I'm sure everybody knows how to do, we introduce implication by proposing a hypothesis and demonstrating that some other term of the logic can be derived from it, right? So in general, the form is, we have some gamma and some other proposition A, so we have some set of propositions that includes A, and that demonstrates B. If we can demonstrate that, then we can rewrite that as A implies B, right? We can also eliminate implication by combining an implication with the premise of the implication. For example, if we have the premises A and A implies B, from this we can conclude B. Is this looking sufficiently familiar? It turns out that there is more than a little conceptual overlap between type systems and logics. So, in logic, basically, many of the sort of basic constructs in logic and in type theory correspond to each other. So, propositions correspond to types. P being a subset of Q corresponds to P having P yielding type Q. P and Q is equivalent to P times Q. Footnote, we'll see this one a little later on when we start doing data structures. So don't worry about it just yet if you don't know what that means, because you shouldn't. Proof of a proposition P is the same as a proof of some term T having type P. And the fact that proposition P is provable is equivalent to the idea that type P is inhabited. That is to say, it has at least one term in it. So, that's kind of interesting. As this property was being investigated, historically speaking, a greater and greater correspondence was found. It turns out that type systems and intuitionistic logics, or just regular logics, mathematical logics, there's enough correspondence there that, like, when a discovery is made in one field, it's generally applicable to the other. The advancement of mathematical logic as a science has yielded great benefits in type theory and vice versa. Essentially, the fields of type theory and mathematical logic can cheat off each other's homework. Type system F, which is a polymorphic type system, it uses quantification over parametric polymorphic types, has its correspondence in second-order constructive logic. Linear logic led to the development of linear type systems, and modal logics have been used to help design frameworks for partial evaluation and runtime code generation. It's not important that you guys know what type system F or linear logic or modal logic is, but no, Nick does not condone cheating. I was using a playful metaphor. Ay, ay, ay. I feel like flashing up the PTSD dog meme with respect to academic dishonesty because of the, you know, we've been dealing with rather a lot of it in the first year class this semester. Anyway, you're not expected to know what modal logic is or what linear logic. Yeah, Mark knows. But, I'm trying to let other people in on the joke, Mark. But yeah, so it's kind of fun. So here's, okay, some of you may be interested in pursuing computer science research at like the graduate or postgraduate level. So I'm gonna give you a career right here, right now. If you can accomplish this, then you probably have a pretty decent career in computer science lined up ahead of you. Step 1, learn how to read papers published by pure mathematicians. Number 2, read up on the most recent developments in mathematical logic by mathematicians. Number 3, design a type system that uses it. Number 4, profit. That's like that would act like there are people who do like that is an actual like line of research, right? You can get into that for a living. Are we even allowed to let other people on the joke? Isn't that technically protected information? I mean, I'm not giving any names, you know. It's just, you know, I'm allowed to speak in like general terms that, oh my, hasn't there been a lot of academic dishonesty this this semester. More detail needed on number 4. Okay. So design your type system, write papers, improve your type system, write more papers, further improve your type system, further write more papers. Write enough papers in order to be able to secure yourself a place as a professor, tenure track in some university somewhere. If your record of publication is sufficiently impressive, that should be okay for you. And then you can start making the big bucks, which is to say, you know, as a person, like before you make professor, you basically make very little money. But yeah, if it's protected, then our children are allowed to know. I don't know what that means. Is that a reference I don't get? Anyway. So, let's talk about erasure and typability. You know what? I feel like this comic right here expresses the popular sentiment towards science right now. The big bucks that Nick is making currently. Right. Oh, for God's sake. Oh! You got me. You got me with your damn object-oriented joke. Very good. I concede. Very, very good. You know. Yes. All right. I will laugh. I will laugh at your joke like the peasant that I am. Okay. So anyway. So let's talk. Let's begin to think about practical considerations, right? Like, up to now, man is accused of stealing baby formula and think he makes money. Yeah. We always pay for all of the baby formula. Yeah, no, if you want to know how much I actually make, I make around $8K per per course that I teach, which isn't that much more than a TA makes. At least not that much more than a grad TA makes. The undergrad TAs, please be nice to them, because they don't make as much money as they should by a long shot. But neither do I, then. But, you know. So, yeah, like, working a full teaching load, I would be making on the order of 60K, which is 3 courses a semester plus 2 in the summer. 64K, I think. And then, if I were hired on full-time, I'd probably be making an extra 20K on top of that-ish. That's like full-time, but not like... That's like a contractually limited appointment type thing. But yeah, I'm although I work a I work basically 65 hour work weeks, I'm still considered part-time. Anyway, so let's consider practical. Let's consider how you would practically do some of this crap, right? So, like, we've been talking about math for so long. Let's give some mental clarity to how this crap would actually be implemented, right? So, type systems. Let's consider for a moment how we would use a type system in a real-world compiler. That is, in a compiled language. I'm not having any of this interpreter nonsense. We're not talking about interpreters. They can go figure out how to do it themselves. So ordinarily, type checking is a pre-processing step. Yeah. Uh-oh, did I lose the feed? Uh-oh. It says I'm still coming through. Uh-oh. I think we're back. Testing, testing. Testing, testing. Okay, that's enough union talk. I am actually unionized. It's QP. I'm under QP Unit 2, and we're currently in contract negotiations, so if they don't go well, guess who's going on strike? Without probably wanting to. Oof. Anyway. So type checking is usually a pre-processing step. You do it before everything, right? Some advanced programs use type annotations during generation as well. Some of them do. Rust, for instance, uses the type system to verify the integrity of pointers. But type annotations and type information in general almost never makes it into the object code. That is the post-compilation result. Typing information is only rarely relevant to execution in very obscure languages. Like, I wouldn't be confident... Like, I would say never, except that I know that Agda exists, and I'm kind of, like, I'm not confident that Agda doesn't work. Like in Agda, the typing information is an essential part of the semantic of the language. It's not just decoration. What is generation? The generation of object code from the abstract syntax tree. You'll learn about it in 3TB3 when you're expected to create one. Maybe. I don't know. Maybe. We'll see. That'd be kind of fun, actually, if I got... I'm pretty sure that the course list for next semester is going to be coming out soon. It'd be fun to teach 3MI3 and then also teach 3TB3 so that I could do, like, here's the theory, now here's the implementation. But, anyway. Erased! from history. At some point during compilation, type annotations are normally removed to improve performance. We can formalize this idea with a type erasure function. So a type erasure, and this is just over our pure lambda calculus. For this topic, we're kind of stepping back into pure lambda calculus for the most part. But so type erasure, all it really does is it goes through and deletes any typing information that might have been bound with the lambdas. And then it recurses through. This operation is recursive traversal of our term, removing typing information from lambdas as we go. Because we have carefully kept our typing system separate from our evaluation semantics, we can remove typing information with no effect on a program's actual execution. That's the reason. That's the reason it's a different relation. We've been very careful. That's one of the things that we've been very, very careful about when we've been designing our semantics so far, is making sure that the typing mechanism doesn't get mixed up with the generation mechanism. Because if it does, you can't easily pull it out and throw it away, right? And you need to be able to throw it away if you want to have an efficiently running program. Like, part of the reason Python's so slow is because it just has all of this typing information that it has to check anytime it tries to do anything. Yes. So, a way of expressing this mathematically is that if we have some term t evaluating to t prime, then the erased version of t will also evaluate to t prime. And we're not going to bother proving that, I think. Yeah. So, we're going to discuss some properties during this topic that we're not going to get into huge proofs for. And that's one of them. So, another interesting property of type erasure is as follows. So, if we have some term t, which we then erase the typing information from and evaluate to some other term m prime, that implies the existence of a t prime such that t evaluates to t prime, and if you erase t prime, you get m prime. Yeah. I mean, Python is good for beginners, and for people who have not yet become sufficiently mature in their programming skill development to understand how helpful a good type system can be. That being said, Python is still a very useful skill. It's still my preferred language for, if I have to do something quickly and I don't really care about doing it well or properly, I'll do it in Python. So, this is to say, if we erase the types from a term t and evaluate it one step, this implies the existence of a typed term t prime, which, once erased, is equivalent to m prime. The gist of these two properties is that it doesn't matter if we erase or evaluate first, we get the same result in either case. This is another way of saying that erasure commutes with evaluation. Remember commutation, the property of commutation? Addition is commutation because 2 plus 3 is the same as 3 plus 2. This is the same idea, but it's applied to relations. Both properties can be proved almost trivially using induction on evaluation derivations. So, I'll leave that as an exercise to the reader, and it's not one of those exercises to the reader that I actually make an exercise to the reader by putting it into the assignment. So how are we doing for time here? We don't really have enough time to get into Church versus Curry. But again, I want everybody to acknowledge how clever I am and how funny this joke is. Nobody got it on my meme feed. Everybody was like, I don't have a sufficient IQ to get this joke and think it's funny. It's like, that's kind of the point of memes, isn't it? It's like, it's so obscure that the humor comes just from the juxtaposition of things that normally wouldn't be juxtaposed, right? Anyway, does anybody have any questions? That curry does look delicious. This makes me want to make curry. Please remember to reply to questions on Piazza. Yes. Yeah, since there's a due date today, yeah, I'll reply to the questions on Piazza. Sorry, it's like normally with the Piazza, you guys have probably noticed this, but like with the Piazza questions, it's like I normally like answer them all at once, you know? Why don't I get paid more? Ask the university. Basically doing the job of a full-time professor. Actually, you know, a lot of sessional professors, perhaps even most of them, wouldn't do what I'm doing with this course and like redo it, you know. So I kind of do it to myself. But yeah, 3 courses is considered a full load for a full-time person in the teaching track. So I have been asked to comment on assignment 7, question 1. So I will comment. It's probably easy. I think... Oh, that's assignment. There we go. This is a funny folder. Basically, this is your tutorial. I was gonna have you do what you're gonna do in tutorial this week as like an assignment, but then it was like, oh shoot, the bloody answers are in the textbook. It's like those are such good questions. So, well-typedness of the omega function. So I'm not asking for a proof here. I'm basically asking you what you think. Right? It's like, can the omega function be well typed? Right? Why or why not? Remember that the omega function is a divergent function, right? So it can be evaluated forever because it just yields itself back up again. So what, like, if that is the case, what implication does that have for trying to apply a type to it? Unfortunately, I can't really say much more than that without giving away the answer. So, yeah. Yeah. In general, sessionals aren't paid enough to care. I think you're going to like my solution then. Ha! Okay. Sounds good. Yeah, and, you know, what with inflation being the way it is, you know, had to confirm you didn't want the world just a rock. Yeah, it's a good way of putting it. If you don't mind, when and why did I decide to proceed to PhD? Ooh, that's a question. So, after I had graduated with my bachelor's degree, which my bachelor's degree is in mechatronics engineering, I worked a couple of jobs, and I didn't really like it. you know, it was partially because I was a stupid kid who didn't even know anything, you know, and it was also partially like I wasn't. I was like looking back at myself after I had graduated with my bachelor's degree. I had not achieved nearly the level of like intellectual or emotional maturity that I now inhabit. So, you know, long story short, I had a couple of jobs and they didn't go particularly well. And, you know, I decided to come back to grad school to do grad school because, like, I was, you know, out of work after the company that I was working for folded. I was working for a solar panel installation company, doing like electrical and mechanical schematics for rooftop solar panel installations, and like speculation about whether the Liberals would be kicked out during the upcoming provincial election was enough to tank demand for solar panel installations, because, you know, the Conservatives were saying they were going to axe the program. So that was enough to send my poor little company that I was working with, that was comprised of like maybe like there was like me, a senior engineer, and like a contractor who did the installations himself with like a crew of like maybe 3 or 4 people, and that was the entirety of the company. And like that speculation on the election just kind of completely tanked everything. So I decided to go back to school because I was looking at all of these job descriptions, and it was like, you know, bachelor's degree required, master's degree preferred. And at that point, like, I had become wise enough from, you know, all of this time I'd spent doing job searches. If you don't have the preferred up qualification, you're probably not in a great position to get that position, because you will be competing with people who have the preferred qualification. So really, you should try to find a job that like fits the bill, like fits your resume very, very closely, right? But anyway, so I decided, well, if they want a master's degree, then I'll go do a master's degree. So I came back to the university. I asked one of my professors that I had during my final years if he had any spots for me, to do a master's degree, and it turned out yes. And so I did a master's degree, mostly. By the end of it, I actually didn't finish the master's degree. I transferred to the PhD program, which actually I think was a mistake. I should have finished the master's degree, and if I wanted to do a PhD after I was finished that process, I shouldn't have made the decision to do a PhD before I finished the master's degree. It's like finish what you start kind of an idea. So, like, I wouldn't recommend anybody do it this way. Although it is actually kind of common in the it's kind of common in the States, actually, for you to be like hired on, well, like brought on board to do a PhD, and then like a master's degree is your consolation prize if you can't manage the PhD. So, you know, it would be terrible. It would be terrible for me at this point, because I came back to the university in 2011. So that you should be able to calculate how long I've been doing. And I transferred into the PhD program like a year and 2/3 in. So you can calculate from that how long I've been doing a PhD. So, yeah. So yeah, my decision to do a PhD was like kind of, the project that I was currently attempting seemed to be going well. and it seemed like reasonably easy. Reasonably easy. It seemed like it would be possible to extend the project as a PhD project in another 3 years of work, and then just, get a PhD out. And, by the fact that it's now been a very long time since that and it's still not finished, you can see how that went. Basically, once I started actually digging into the problem, manifold were the problems that I encountered. Basically, in order to be able to do anything practical with this translator that I was building, I had to completely redo the semantic that I was working off of, right? Like, so my original master's work was, I had there had been this manual translation process that had been published by some people out of the University of Manchester. Yeah, you don't worry, Mark, you'll get an answer out of me, I'm sure. Some people out of the University of Manchester published a paper about a manual translation process between, like, a theorem prover and a hardware language. And my master's work was essentially to take their manual process and make it an automated process. And it was fine. It worked pretty well, actually. I was able to reproduce their work reasonably easily. The only problem is, once I started trying to apply that methodology to, shall we say, case studies of more practical significance, I found out that it's hard for me to say something that isn't like I found out that I had been lied to. You know? Like, the semantics that they presented were completely inadequate for demonstrating anything above the level of a very small toy example. And there were some, like, very, very important language constructs that, like, they just did not address at all, and they made no attempt whatsoever to even understand the semantics of the existing language. They sort of used, they like built their semantics off of their understanding of one phrase in the documentation, and that was as far as they were going to take it. And this guy got a PhD for this. So here I am doing a PhD in software engineering, like 8 years later, and still, like, trying to get the bloody thing working, but it's like, it's difficult because to some degree, because I'm doing engineering, the value of the project is to some degree contingent upon whether or not the bloody thing works and the degree to which it works. So yeah, that's kind of the story of my PhD. I hope that you enjoyed it. Man. So yeah, that's kind of, like, at a certain point with it, like, the reason I'm doing all this teaching now and, like, not doing the research is, like, as, you know, I am working on the research. It's just, you know, most of my time is spent on the teaching. At a certain point, like, when you've been doing something long enough, you know, you kind of have to move on to the next thing, or else you literally go insane. But, yeah. Okay. Well, anyway, take her easy, folks. I'll answer the Piazza questions. And, you know, stay cozy.